Hello students, welcome to the Power Electronics. In this section we are going to learn experiment on single phase AC to AC voltage controller. In this AC voltage controller we are using as a TRIAC with R and RL load. Circuit diagram of TRIAC using R load. TRIAC symbol, TRIAC as in a 3-terminal, anode 1, anode 2 and gate terminal. Now in simulation there is no TRIAC device, so with the help of the two thyristors anti-parallelly connected, it works as a TRIAC operation. Now here in the circuit shown using two thyristors with R, that is a equivalent of TRIAC circuit diagram with R load and waveforms. Circuit diagram of TRIAC using R L load. So instead of R, it connected as a R and L. So these are the model waveforms. MATLAB Simulation Implementation on R load. Input voltage 50 peak equals 35.35 RMS and frequency 50 Hz. R is 12.5 ohm. This is a model of Simulink model using TRIAC. MATLAB Simulation Implementation on RL load. Input voltage 50 peak equals 35.35 RMS and frequency 50. R is 12.5 ohms and L is 6 millihenries. Pulse generator configuration. Pulse type time base. Time use simulation time. Amplitude 1, period 0.01. Pulse width 5%. Phase delay, so here it is mentioned 30, means that is your firing angle 30 degrees. Instead of 30 you will place as a 0, that is firing angle 0. MATLAB 19A simulation block and path. So these are the block required. Using this path, so we have to select all the blocks. Now we will do the simulation on the MATLAB. Double click on MATLAB icon on the desktop. After opening MATLAB, double click on Simulink library, Simulink. Double click on blank model. Now your model is opened with untitled name. So save this file with some file name. For this, go to File, Save As, EXP 9. Now your model is saved with EXP9. Here you are designing your simulation models. For this you need a block. For this, go to library browser. In Power Electronics, path is Simscape. Under Simscape, electrical, specialized power system, fundamental block. In that, select Power GUI. Add to model, select electrical sources. In that, select AC voltage source, add to model. Select elements. In that, select series RLC branch, add to model. Measurements, voltage measurement, current measurement, add to model. Power Electronics, select as a thyristor, add to model. Now mean and RMS block, control measurement. In that measurement, select mean, add to model. Select RMS, add to model. In Simulink, under this commonly used block, so you need a scope and display. Under Simulink, under this sinks, select as a scope, add to model. Select display, add to model. Select sources. In that pulse generator, select add to model. We got we selected all the blocks. Now we'll separate all the blocks. Now double click AC voltage source. Peak amplitude give as a equivalent to RMS 35.35 volts. Apply and OK. Now you can select one more thyristor. Select, copy, place in anti-parallel. So Control plus R. Label it as a T1. T2. Now first T1 anode to T2 cathode, T1 cathode to T2 anode. Now place the current measurement here, and from AC voltage source one terminal to current measurement plus terminal, current measurement negative terminal to T1, T2 anode and cathode joint point. Select series RLC branch. In that, select as a R. Resistance value is 12.5 ohms. Rotate this resistor by pressing Ctrl plus R. It also required as a current measurement. And voltage measurement. Resistor other terminal to current measurement plus terminal, current measurement terminal to AC voltage source other terminal. Now this voltmeter connect across the AC voltage source. Then it will be measured as a input voltage. This voltmeter connect across the load plus one load of one terminal, negative to load of other terminal. Now double click the pulse generator. Amplitude pulse type is time base. Time, use simulation time. Amplitude 1, period 0.01 seconds. Pulse width 5%. Phase delay, first we'll give as a 0, multiply braces start 0.01 divided by 180 degrees. Now here 0 nothing but your firing angle is 0. Apply and OK. Connect this pulse generator to T1 gate terminal. Same pulse generator terminal to T2 gate terminals. Now can double click the scope. I will increase the number of input port to scope. For this, go to configuration properties, number of input port to 4, layout, apply and OK. Now first we will connect as a input voltage, input current, output voltage and output current. Okay, double click mean. Fundamental frequency as a 50 Hz. In RMS block also fundamental frequency 50 Hz. Add one more display block to mean, joining mean to display, mean to output terminal of voltage, RMS to output terminal of voltage measurement. Now you can see, if you want to see the pulse, how it is generating, you can add one more scope to from pulse generator. Select one more scope. For this Simlink commonly used block, select scope, add to model. Now save your model by pressing save button and change your simulation time to 0.5 seconds. Now run your simulation by pressing run button. Now your results has a firing angle is 0. Run it. You can add mean current and RMS current also. Mean to output current, RMS to output current. Run your simulation by pressing run button. Why? Because we added mean and RMS blocks of currents also. Run it for simulation. Now you can observe the when alpha is 45 degrees. Next, alpha is 90 degrees. Instead of 45, give as a 90 value. Firing angle is 90 degrees. Save your model and run your simulation by pressing run button. So if you are unable to see all exactly, so you can reduce your simulation time to 0.1 second. Run your simulation. Now it has exactly 90 degrees, this one, 0 to 180 in that 90 degrees. Firing angle is 90 degrees. These are the output waveforms. Take a screenshot, save in the folder. Next, firing angle is 120 degrees. Apply and OK. Run your simulation. Results of firing angle 120 degrees. Now you can observe the output voltage at 120 degrees start to conducting. Take a screenshot of this one. Firing angle is 120 degrees. Save in the folder. Now this simulation, take a screenshot of this one, your circuit diagram as a R load. Now we'll do the RL load. So double click, select series RLC branch. Double click series RLC branch. Branch type select as a RL. L is 6 millihenries. Apply and OK. Now it works as a RL circuit. Now you can, in the pulse generator, instead of 120, give as a 0 as a RL circuit. Firing angle is 0. Save your model. Run your simulation by pressing run button. Now we'll see the results in the scope. When firing angle is 0, you got an output like this, waveforms like this. Take a screenshot and save in the result some folder. Now change it firing angle to 45 degrees. Apply and OK. Run your simulation by pressing run button. Now you can observe when firing angle is 45 degrees. voltage, output voltage at 45 degrees. Take a screenshot and save in the folder. For different firing angle, now give as a 90, again run your simulation. When firing angle is 90 degrees, these are the output voltage. Now take a screenshot, save in the folder. Now change it to firing angle to 120. Apply and OK. Save your model. Run your simulation by pressing run button. Now output voltage at firing angle is 120 degrees. Now these waveforms, take a screenshot of this waveform and save in the folder. For different firing angle you are saved. Take a screenshot of your circuit also. Hardware implementation on R load. For this you require as a power module and firing circuit, TRIAC device, resistive load and digital storage oscilloscope. In power module will give you as a 3-phase supply, single phase supply and DC supply. In that you have to choose as a single phase supply and give the phase terminal to your anode terminal of TRIAC, cathode terminal to load 1 terminal. Now load between black and blue as a 50 ohm. So 50 by 4 resistor connected in parallelly, that is equivalent value R is equal to 12.5. Or other terminal is given to supply neutral terminal. Now across the R we will measuring the output voltage. When you changing the firing angle, when we are moving this knob, firing angle is applied on the TRIAC. For different firing angle you can save your waveforms. When changing firing angle 0, 90, 0, 45, 90, 120 degrees. Hardware implementation on RL load. For this power module is required, firing circuit, TRIAC device, resistive load, R value is 12.5 ohm, inductive load, L value is 6 millihenries. So in previous circuit, instead of R, can connect as a R and L load in series. Now we'll observe the waveform output voltage in the digital storage oscilloscope. Now we'll do the hardware on AC voltage controller using as a TRIAC with R and RL load. For this hardware equipment required as a power module and single phase firing circuit, TRIAC device, resistive load and inductive load and digital storage oscilloscope. In power module, the power module will give 3-phase supply, single phase supply and DC supply. In that we have to choose as a single phase supply. Now we'll make the connection from the single phase AC voltage source to input of MCB, phase to phase, neutral to neutral. From the output of MCB phase to TRIAC anode terminal, TRIAC cathode terminal to load of 1 terminal. Now from the load second terminal to output of MCB neutral terminal. Now we'll make the resistance as a equivalent 12.5. For this select as a 50 ohms connected in parallelly, then we'll get as a resistance equivalent as a 12.5. From all 50s join. and remaining zeros also join. Now between 0 and this 50 terminal, now 4 resistors are connected, 50 ohms resistor connected in parallelly. Now we'll get between black and red terminal, the resistance value is 12.5 ohm. Now you can observe this probe terminal as a positive terminal, this has a negative terminal. Across the resistance, now we are measuring is the voltage in the digital storage oscilloscope. Now we'll switch on 3-phase supply and switch on meter switches, switch on power module MCB, switch on AC voltage source, switch on SCR diode power module MCB, and one more thing is here you have to turn on the TRIAC. The gate pulse is required from the firing circuit to will apply as a one gate pulses to firing TRIAC gate terminal. Now increase the voltage . 35.3. One more thing is make it the single phase firing driver circuit should be on. Now adjust the voltage to 35.3 and switch on firing circuit of driver switch should be on. Now you got an output voltage when firing angle is 0. At firing angle is 0, you can observe the mean and RMS voltage by pressing measurement button. Now cursor should be off and press measurement button. Now alpha is 0 position. This waveform you have to capture in the PC. Open choice desktop and select instrument, select USB and OK. Now the instrument is identified and by pressing get screen button the waveform will be captured in the PC. Now this waveform you have to save in the folder when firing angle is 0. Now we'll change the firing angle to 45 degrees. Using this knob, adjust the firing angle to 45 degrees. Now you can observe the waveform and you have to measure using the cursor. We have to find the delta T by press cursor button. Now we'll measure the wave delta T. Now it is as a 2.4. Adjust the two cursors. Now cursor 1 0, cursor 2 also 0 volts. It is reference on the exactly ground point. So now we'll get as a delta T is 2.4. We'll consider as a firing angle is 45 degrees. When alpha is 45 degrees, now we'll measure the mean and RMS voltage by pressing measurement button. Now we got an RMS and mean. So that waveform you have to capture in the PC by pressing get screen button. Now you can observe between these two cursors the delta T is 2.5 milliseconds, nothing but 45 degrees. And we'll do the firing angle to 90 degrees and again change the firing angle to 90 degrees. The delta T is 5 milliseconds. Now you can observe the delta T. Now cursor 1 0 voltage and cursor 2 0 reference voltage. Now you can observe the delta T 5 milliseconds is nothing but your firing angle is 90 degrees. When alpha is 45 degrees or firing angle is 90 degrees, now we will measure the mean and RMS voltage by pressing measurement button. Now when alpha 90 degrees, capture the waveform by pressing get screen button. Okay, between these two cursors the delta t is 5 milliseconds at 90 degrees of firing angle, RMS and mean, and these waveform you have to save in the folder. Now firing angle to 120 degrees, adjust the firing angle knob to 120 degrees is nothing but the delta t is 6.6 milliseconds. Can press the cursor button. Now we'll observe the delta t. Now cursor 1 on 0 reference voltage, cursor 2 0 reference voltage, delta t is 6.6 millisecond is nothing but firing angle is 120 degrees. When in firing angle 120 degrees, observe the mean and RMS. RMS voltage, you got any values, and that waveform you have to capture in the PC by pressing get screen button. Now you can observe the RMS voltage, and between these two cursors the delta t is 6.6 milliseconds, nothing but firing angle is 120 degrees. Now AC voltage controller with R load we are done for firing angle 0, 45, 90 and 120. Now we will do the AC voltage controller with R and RL load. For that again firing angle bring back to 0 and make it circuit off and remove one of the resistive load terminal, connect from resistive removed terminal to inductor terminal, inductor other terminal connect to the MCB output of neutral terminal. Now between the black and red terminal the inductance value is 6 millihenries and resistance value is 12.5 ohm. Now we are doing on RL circuit. Again switch on your MCB, apply the voltage to circuit and adjust the voltage to 35.3 or 4. Okay. Now your firing angle is 0. Now you can observe the first by using cursors for completing one off cycle as a delta t 10 millisecond. When firing angle is 0, as a off cycle as a 180 degrees taking time is 10 milliseconds. So you can calculate according to for 45 degrees, 90 degrees and 120 degrees. This value by 4 you will get as a 2.5, that is nothing but 45 degrees, and this value divided by 2, then 180 by 2 equal 90 degrees, and this value divided by 3 you will get as a 120 degrees, that is 6.6 milliseconds. So like that from this one we are calculating the firing angle in the angular position to time. Now when it is in firing, now this is as a firing angle 0 and press measurement button. When firing angle is 0 you got an RMS, only RMS value you can observe. This now this waveform at R and L when firing angle is 0. This waveform you have to capture in the PC by pressing get screen button. Now RMS value is 33.0 volts when alpha is 0 degrees. Change the firing angle to 45 degrees. So we'll use the cursors, we'll observe the delta t and use second cursor. Now delta t is 2.2, so we adjust it to 2.4 or 2.5. Okay, so we are not getting exactly 2.5, so it is coming in even number. So now we'll consider as a 2.4 millisecond as a 45 degrees. When alpha is 45 degrees, now you can observe the mean and RMS voltage by pressing measurement button. Now you can observe the RMS voltage. That waveform you have to capture in the PC by pressing get screen button. Now between these two cursors the delta t is 2.5 millisecond. Now this is the RMS voltage. This waveform you have to save in the folder by pressing save as button. It will be saved in the folder. Now firing angle to 90 degrees. So use cursors. We'll measure the delta t. Now you can observe cursor 1 0 reference voltage, cursor 2 0 reference voltage, and delta t is 5 millisecond. Nothing but your firing angle is 90 degrees. At 90 degrees, you can observe the RMS voltage by pressing measurement button, and this waveform you have to capture in the PC by pressing get screen button. Now between these two cursors delta t is 5 milliseconds. Now we got an RMS is this much. Otherwise you can place the cursors, and this waveform also you have to capture. If you know the exactly cursor, the delta t also you can observe. See, the delta t is 5 millisecond between these two cursors. Here you are unable to see the RMS values, measured values. Here we are unable to see. Here we are observing only delta t using the cursors. Now we'll adjust the firing angle to 120 degrees. I am changing to firing angle to 120. So how we know that 120 degrees, the delta t, using the cursor, the delta t as a 6.6 milliseconds. So you can observe cursor 1 0 reference, cursor 2 0 reference. Now delta t is 6.6 milliseconds. Then the firing angle position is 120 degrees, and measure the RMS voltage by pressing measurement button. We'll use cursor first. That waveform you have to save by pressing get screen button. For understanding the how much cursor we placed here, you can observe the between these two cursors the delta t is 6.6 milliseconds. Now you can cursor 1 at 0 voltage, cursor 2 also 0 volts. Then we have to place like that. Otherwise you are moving the cursors somewhere, that delta t is not correct time. Now press measurement button, find the RMS voltage and get screen at firing angle 120 degrees. Now at 120 degrees the RMS voltage is we got an 8.72 volts. Now we are done AC voltage controller with R load, using TRIAC with R load and RL load, 0 firing angle, 45 degrees, 90 degrees and 120 degrees we are done. Now again bring back to your procedure to bring back to 0, firing angle to 0 position, and circuit make it of MCB and reduce the voltage to 0 volts, AC voltage to 0 volts, and make it off your single phase AC voltage source to off, make it off power module MCB off, and switch off your main 3-phase supply MCB off. Observations and results for R load. Now we already saved all the files in the folder. So here you have to attach the waveform. At firing angle is 45 degrees and attach the waveform of output voltage from the experimentally at firing angle is 45 degrees. Simulink and experimentally these values you have to place in the tabular column for different 0 degrees, 45 degrees, 90 degrees and 120 degrees. Observations and results for RL load. Attach the circuit diagram of single phase AC to AC voltage controller with RL load in MATLAB Simulink. We already saved that screenshot of the circuit diagram. Here you have to attach the waveform of input voltage input current, output current in simulink at 45 degrees. Here you have to attach. Attach the waveform of output voltage at firing angle 45 degrees experimentally from the DUSO. Here you have to attach. Calculate performance parameter with RL load, simulink and experimentally. When alpha is 0 degrees, place the values of output voltage, RMS output voltage, RMS output currents like 45 degrees, 90 degrees, 120 degrees. Thank you.